Now let's prove the limit of sine theta over theta as theta approaches 0 is equal to 1. So suppose we have a triangle ABC. Now, like any triangle, the area of triangle ABC is given by 1/2 times the base times height. For this case, the base of triangle ABC is the length is AB, the line segment AB, or side AB. And the height is given by CD, where D is a point between A and B such that CD is perpendicular to AB. Okay? So therefore, we have the area of triangle ABC is equal to the product of 1/2 the length of AB and the length of CD. Now, suppose we have a sector ABC on the circle centered at point A. So for this case, the area of the sector is given by 1/2 times the square of the radius times the value of theta in radians. Okay, so theta is the angle formed by the sector. Okay, and the length of the radius, let's say we use r to designate or to denote the length of the radius. So we'll have 1/2 times r squared times theta. Now let us consider the unit circle O. So when you say a unit circle, its center is at the origin. Let's denote the point. Let's denote it as point O. And since it's a unit circle, then the radius will always have a length that is equal to 1. Okay? Now, point B is a point of intersection of the circle and the positive x-axis. So point B has coordinate 1, 0. Now, any point on the circle will have a coordinate cosine theta, sine theta, where theta is the angle formed by the line connecting the origin and that point, point A, and the x-axis. Okay, so this is our theta. Now, this creates a sector. A sector AOB. Okay. Now, we are also able to create a triangle from this by connecting point A to point B. So we have a triangle AOB. We can also produce another triangle when we create a line that is perpendicular to line OA. Okay? Now let's say the point of intersection is point D. So D will have a coordinate, let's say 1D. Why is it 1? Because the base is side OB, which is the radius of the circle, so the length is 1. Now let's denote the height, or let's denote this part, the height of this point, or the y coordinate of this point as D. We do not know it yet. But we are able to create a triangle DOB. Now visually, we can see that the area of triangle AOB, the one in green, is less than the area of triangle of the sector AOB, the one in blue, which is also less than the area of triangle DOB, the one in purple or in light blue. Okay. Now suppose, okay, so now let's locate the height, or let's determine the height of triangle AOB. That is, we create a line from A perpendicular to the base, which is side OB. And let's denote this point, the intersection of the base and the perpendicular and the line that's perpendicular to it, as point C. So the x-coordinate of point C is cosine theta. Okay? But the y-coordinate is 0 because it lies on the x-axis. So therefore, we have this inequality. 1/2 times the base of AOB, which is the length of OB, times the height, which is the length of AC. For the sector, we have 1/2 times r squared, or the radius, times theta in radians. Then the area of triangle DOB would be 1/2 times the base, which is OB, times the height, which is DB. Okay, so when we substitute the values, the given values, so since we have a unit circle, then the length of OB from the origin to the point on the circle is 1. It's the radius. Then the length of AC, the height of AC, or the length of AC, is sine theta. That's why we have this. Okay, so r is 1, so r squared is 1, so we have 1/2 times 1 times theta. For DOB, we have 1/2 times OB. OB is again the base, which is the radius of a circle, so it has a length 1, and then DB is Z. So we have this. So let's try to simplify. Then we have 1/2 sine theta less than or equal to 1/2 theta times 1/2 Z. 1/2 is common, so we can factor it out. So we'll have sine theta less than theta, which is also less than Z. So let's establish this for us to find Z. We have the inequality sine theta less than theta less than Z. And now we will solve for the value of Z. Okay, so let's look at triangle AOC. I'll color it yellow so that it's obvious. And then let's compare this with triangle DOB. Okay, so these two triangles, triangle AOC and DOB, are similar triangles. So when we have similar triangles, we can take the ratio of the length of their corresponding sides. So the height, so that's side DB corresponds to the height of the smaller triangle, which is AC. The base of the bigger triangle, which is OB, corresponds to the base of the smaller triangle, which is side OC. So we have this ratio. DB over OB equals AC over OC. Now the length of, or the height, DB, or the length of side DB is equal to Z. The base of the bigger triangle is equal to 1. And then the height of the smaller triangle is sine theta. And then its base is cosine theta. So when we substitute these values to our ratio, we'll get Z over 1 is equal to sine theta over cosine theta. And now it's very easy to get the value of Z. We see that Z is equal to sine theta over cosine theta, or Z is tangent theta. Okay, so let's put down the things that we have derived for easy reference. We initially found that theta is between sine theta and Z, and that Z is equal to tangent theta. So we say that theta is greater than sine theta and Z is greater than theta, or sine theta is less than tangent theta. So we have sine theta less than theta less than tangent theta. So when we divide the inequality by sine theta, what will we get? We will get sine theta over sine theta less than theta over sine theta less than tangent theta over sine theta. So if you look at this, we'll have the squeeze theorem to prove the value of theta, to prove the limit of theta over sine theta as theta approaches 0. Okay, now let's work on tangent theta over sine theta. Tangent theta is sine theta over cosine theta. So when we divide it by sine theta, what will we get? We will get 1, we will cancel theta, sine theta, so we'll get tangent theta over sine theta equal to 1 over cosine theta. So we have, since sine theta over theta is 1, we have 1 less than or equal to sine equal to theta over sine theta less than 1 over cosine theta. If we take the limit as theta approaches 0, we get this. No. So let us look at the end functions for us to know the limit of sine theta over, or for us to know the limit of theta over sine theta. 1 is a constant function. So by the constant law, we know that the limit of 1 as theta approaches 0 is 1. Okay. Now, 1 over cosine theta. Cosine is a trigonometric function, but when theta is 0, cosine is 1. So my guess here is that the limit of 1 over cosine theta as theta approaches 0 is equal to 1. So let's look at the graph of cosine theta. Okay, so let the value of theta approach 0 from the left and from the right. Now observe the graph. The graph leads to having a value of cosine theta equals 1. So therefore, we say that the limit of cosine theta, theta approaches 0, is equal to 1. So we have this. 1 over 1 is equal to 1. Again, this is because the limit of the denominator is 1, from what we've shown earlier. So therefore, we have the limit of sine theta, the limit of theta over sine theta as theta approaches 0 is greater than 1 and less than 1. So therefore, we say that the limit theta over sine theta is squeezed between the constant function 1 and the function 1 over cosine theta. So by the squeeze theorem, we say that the limit of theta over sine theta, theta approaches 0 is equal to 1. If you take the reciprocal, so the reciprocal of the limit is just equal to, since the limit of this is 1, so the limit of its reciprocal is 1. So therefore, we have the limit of theta over sine theta, theta approaches 0 is equal to 1, and the limit of sine theta over theta as theta approaches 0 is equal to 1. So with the use of the squeeze theorem, we were able to show the following two theorems. That the limit at theta approaches 0 of theta over sine theta is equal to 1, and that the limit of its reciprocal, theta approaches 0, is also equal to 1.